In this chapter, we're going to take a look at descriptive statistics. Descriptive statistics is all about organizing and summarizing data so that we can broadly and quickly describe it. You'll likely recognize some descriptive statistics right away. For example, mean, median, and mode are all descriptive statistics that we refer to as measures of central tendency. There are some less commonly used descriptive stats that can offer us different insights such as variance, standard deviations, skewness, and kurtosis. These can be categorized as either measures of dispersion or variability. This chapter will explore these categories of descriptive statistics. We'll explore other terms useful in our initial exploration of a dataset, terms that can describe the number of variables or the relationship between variables. Finally, we'll put this knowledge to the test by exploring some real market data in Excel. We'll apply some of our favorite tools and functions to pull relevant descriptive statistics quickly, so we can summarize features of our dataset efficiently and accurately. Let's get started. Measures of central tendency attempt to identify the central position of our data. There is the mean, which tells us the average of our data, median, which tells us the middle number if we arrange our data from the smallest value to the largest, and mode, which describes the most frequently occurring number. If the distribution of our data looks like this, the mean, median, and mode should all fall in the middle. But in most other scenarios, these measures are not interchangeable. Each tells us something different about our data, and we may prefer one depending on what we are trying to understand. One of the ways in which these three measures are different is in how sensitive they are to outliers or skewing. As our data skews left or right, the mean moves with that skewing. The medians move as well, but to less of a degree, and our mode remains right at the peak. Taken together, they can be helpful for understanding the skew of our distribution. If we see our mean, median, and mode line up, so our mean is the smallest and the mode is the largest, it indicates our data is skewed to the left. Or when the pattern is reversed, it would indicate that our data is skewed to the right. Measures of central tendency attempt to identify the central position of our data. There is the mean, which tells us the average of our data, median, which tells us the middle number if we arrange our data from the smallest value to the largest, and mode, which describes the most frequently occurring number. If the distribution of our data looks like this, the mean, median, and mode should all fall in the middle. But in most other scenarios, these measures are not interchangeable. Each tells us something different about our data, and we may prefer one depending on what we are trying to understand. One of the ways in which these three measures are different is in how sensitive they are to outliers or skewing. As our data skews left or right, the mean moves with that skewing. The medians move as well, but to less of a degree, and our mode remains right at the peak. Taken together, they can be helpful for understanding the skew of our distribution. If we see our mean, median, and mode line up, so our mean is the smallest and the mode is the largest, it indicates our data is skewed to the left. Or when the pattern is reversed, it would indicate that our data is skewed to the right. Measures of dispersion, or measures of variability, help us understand how dispersed or spread out our data is, which in turn lets us know how meaningful our mean is. Put another way, how far a random result is likely to fall from the mean. If our data is widely spread, a result far from the mean becomes more likely. When making inferences, this can mean more uncertainty. The most simple measures of dispersion are the minimum, or the smallest value, the maximum, or the largest value, and the range, or the distance between these 2 points. The minimum, maximum, and range can help us to understand the best and worst case scenarios, and the range would help describe the entire spectrum of possibilities. Quartiles are another way of dividing distributions. Whereas the median is just the middle of our data, quartiles take the middle of that middle, dividing our dataset into 4 quarters. This method is popular with economists, who use quartiles to study policy effects at different income levels. By looking at changes in income across the first, second, third, and fourth quartiles, they can provide a more nuanced picture of a changing economy, which speaks to the experiences at each quartile. Variance is a measure of how spread out all of our data points are. More specifically, variance measures how far each number in the set is from the mean, and thus from every other number in the set. It is calculated by taking the differences between each number in the dataset and the mean, then squaring the differences to make them positive, and finally, dividing the sum of these squares by the number of values in the dataset. The advantage of variance is that it treats all deviations from the mean as the same, regardless of their direction. By squaring the deviations, they cannot sum to 0 and give the false appearance of no variability in the data at all. We've learned methods for describing the central tendency of our data and the dispersion of our data. So let's start looking at ways to describe the shape of our data. Remember this chart from earlier in the course? This bell-shaped curve is what we call normally distributed, also known as the Gaussian distribution. The normal distribution shows up a lot. Heights, blood pressure, and IQ all follow a normal distribution. Data also comes in distributions that are not quite normal, even if some of them appear to be normal. Something about the normal distribution is quite specific, not just the shape. The key features are that it is symmetrical around the mean. The mean, median, and mode are all the same in a normal distribution. And our distribution also has tails on both sides, which approach, but never actually touch, the x-axis. By applying the empirical rule to any normal distribution, we can determine the proportion of values that fall into certain ranges of the mean. 68% of our data points fall within 1 standard deviation. 95% fall within 2 standard deviations, and 99.7%, almost all of our data, fall within 3 standard deviations of the mean. We're going to be seeing a lot of the normal distribution. This is because an underlying assumption in a lot of statistical tests require that our data is normally distributed. This may sound like a big limitation, but it really isn't. We'll explore why a bit later when we discuss the central limit theorem. While the normal distribution occurs regularly, non-normal distributions are also common. Let's review another measure that can help tell us more about the shape of a distribution. Curtosis is a measure that focuses on the weight of a distribution around the mean or around the tails. Distributions that are mesocurtic look like a normal distribution. In a platycurtic distribution, the weight of the distribution is spread around the mean with very little distribution in the tails. And leptocurtic distributions are more peaked, with very fat tails, and therefore a larger number of outliers as well. In finance, the distribution of assets returns are normally not normal. The S&P 500, for example, tends to be leptocurtic. Real estate, bonds, commodities, and other investments that have less variance tend to be platycurtic. So far, we have looked at normal distributions, as well as some distributions that are symmetrical and are close to a normal distribution. Next, let's take a look at some distributions that aren't symmetrical at all. As mentioned earlier, data comes in distributions that are not normal. Data can be bimodal, parabolic, flat, or just about anything. Asymmetric data distributions are common and are often described in terms of skewness. Skewness describes where the data is clumped and where the outliers tend to occur. With negatively skewed distributions, most of the outliers tend to be to the left of the mean, pointing in the negative direction, while most of the data tends to be clumped to the right of the mean. With positively skewed distributions, the outliers tend to be to the right of the mean, with data clumped on the left. In this video, we're going to explore some data in Excel using the Data Analysis Tool Pack. Before we begin, let's make sure we have the tool pack added. Let's go to File, and then Options down here at the bottom. Then, find the add-ins from the left menu. At the very bottom, it will say Manage. We're going to select Excel add-ins from the drop-down here, and then we're going to hit Go. Make sure this Analysis Tool Pack is selected. If you don't see it as an option, you might need to click Browse and look for it. Once it's selected, hit OK. You may be prompted that it's not installed, and if so, click Yes to install it. In the Descriptive Statistics Excel file, we'll start by looking at our data. Here, we have 5 years worth of data from the S&P 500 index, taken from 2017 to 2022. A good practice when analyzing data within Excel is to never mess with this original data. Instead, we want to make copies of what we want to edit. So let's copy all of our data from here, and we'll paste it into our first sheet, this Univariate tab. For this analysis, we want to look at the price column as well as the percent change. So let's clean this up and delete the other columns that we don't need. Now we're ready to start with our analysis. Let's start by making a line plot to show the overall trend in price for the period. Line plots typically show a time series. With these charts, the x-axis tends to be the independent variable. This is the variable whose value doesn't depend on anything else, and this is almost always a measurement of time. Time doesn't change based on the change in price of the S&P 500, making it an independent variable. On the y-axis, you'll typically place your dependent variable, a variable whose value is dependent on the independent variable. Our price does depend on the date. So let's select the date and the price columns. We'll go to Insert on the ribbon and hit Recommended Charts. Let's grab the line chart from here and select OK. I'm going to reposition the chart and make it a little bit bigger. We can see from our chart here that there's a general uptrend in our price, which is no surprise. Index investing is often promoted as good at following the general market, and the general market tends to go up. Now that we have an idea of our trend, let's look a little bit deeper at some descriptive statistics. You're probably aware that there are individual Excel functions to get some descriptive statistics, such as a mean, a median, or minimum and maximum values. Instead of using these functions, we're going to get all of our descriptive statistics at once using the Data Analysis tool. Let's head to the Data tab on the ribbon, and then we'll find the Data Analysis all the way on the right here. Once we click that, from the drop-down menu, we're going to select Descriptive Statistics and hit OK. On this input range, let's hit this button, and we're going to select our price change column. We do have labels in the first row, so make sure that that box is checked. Let's select an output range on our current sheet. So let's select cell E2. And finally, we want to make sure that we've checked the Summary Statistics box, and we'll hit OK. And there we have all of our descriptive statistics. Let's make this a bit easier to read. I'm going to change the data type of some of this output. So since our original data was in percentages, let's convert some of these metrics into percentages as well. So let's take the mean, standard error, median, mode, standard deviation, and the range, the min and the maximum as well. We'll change this to percent, and we'll go to 3 decimal places. So what do we actually see here? Well, we see that the mean is slightly positive at 0.037%, and this makes sense as we saw a general uptrend in the change of our price. The median is 0.084%. Recall what a difference between a mean and a median signifies. it means that there is some skewness in our data. And we can see that this skewness measure down below confirms this. For skewness, a value of 0 is the absence of any skew. A negative skew measure means most of our values are more clustered on the positive side. And another way that we can see this skew is with a histogram. A histogram is similar to a bar chart. It provides an approximate representation of the distribution of a dataset. To create a histogram, data is put into bins. So let's try this out. First, I'm going to move our price visual over a little bit to give us a bit more space. And now let's select our price change column, go back to Insert, and any versions of Excel that are 2010 or later should have an option for a histogram. So let's select a histogram here. And let's resize it. So let's double click on the axis to bring up some options, and we can see that our bins have been created automatically for us. And they're quite granular. We have quite a lot of bins, and we can see that on the very left-hand side, our bin range is between -11 to -10.5%, and on the very right, it's from 8.84 to 9.27%. So we can adjust either the bin width or the number of bins as well. So let's change our bin width to 0.01 or 1%. Now we can see the distribution in our data. The two most common price changes range between -1 and 0 and 0 and 1% change. We've essentially created categories from this price change column based on the ranges that we're seeing in our data. Let's click on the bars in the visual, and let's add a data label. So we can see that over to the right-hand side of our histogram, we are seeing a few more positive points, very slightly, but more positive points than over to the left-hand side of our histogram over here. Another interesting point from the histogram is the kurtosis. A normally distributed kurtosis has a value of 3. And since this is over 3, we can look at our kurtosis measure over here at 11.8. We see that it's more clustered towards the middle and has fatter tails with some outliers that are very far out. As for the range, from the lowest to the highest value, we see a difference of 20 percentage points. The lowest value on any given day is roughly around -10.9%, while the maximum is a 9% increase. We looked at the range of our data with our histogram here. However, on a larger time frame, our range would not be exactly like this. It could contain larger outliers on both the negative and positive side. So if we make any investment decisions around the idea that on a given day, the market can only go down -11%, and it happens to go much lower than that, we could be in trouble. A way to visualize the distribution and outliers of our data is with a box and whisker plot. And these plots show us the median, quartiles, and relative maximum and minimum of our data in graph form. Let's create this plot for the change in price column. So I'll select this change column, go to Insert on the ribbon once again, and this time select a box and whisker plot. Let's resize our histogram above here, and then we'll take our box and whisker plot and put it just below. The median in our box and whisker plot is represented by the horizontal line in the middle of the box. Sometimes the average is indicated with an X. And if I drag and resize our box plot, we can see that the X and our median line are really close together. And this is confirmed by looking at the mean and median from our descriptive statistics. The whiskers in our box and whisker plot show us the extremes of our range, while outliers that we may not have included are shown as dots lying outside of that range, on both the positive and the negative side. Each dot represents a single observation or row from our data. Let's take this chart, copy it, and paste it over here as an image. And for now, I'm just going to take our original visual and drag it out of the way next to our line chart. Now let's take that image and let's rotate it 90 degrees. And now our box and whisker plot is aligned with our histogram above. I'm just going to resize this. Now that we've resized the image to align the percentage points from our box and whiskers plot with our histogram, we can see how it lines up. Both plots help us to understand the distribution of our data. They're a bit funny looking, but box and whiskers charts convey a lot of information in a very small space. We see the central tendency of our data, the range, and we can even get a sense of the shape of our data. Its small size makes it great for when we have a lot of distributions which we want to compare. In later chapters, as we get into hypothesis testing and inferential statistics, we'll jump back into Excel's data analysis tool to run some other analysis together with new datasets.